Okay, hi everybody. Welcome to lecture 2 of the geometric discrepancy theory course. Today I will talk about a slightly different topic. I will talk about discrepancy on the sphere. This lecture is almost independent from the first one. If you missed it or if you didn't quite follow, you can start from scratch here. Okay, so as I said, I will talk about points on the sphere, discrepancy on the sphere. We will prove one pretty famous theorem about discrepancy of points on the sphere, and along the way, we will actually learn quite a few interesting related topics. Okay, so let me start with a little table that relates things that we did in the last lecture and things that we are going to do. So we discussed discrepancy last time, and we essentially discussed this situation here, the situation of axis parallel rectangles. And we actually proved both of these theorems. We proved that the extremal discrepancy is bounded below by log n in this case, and the L2 version is bounded below by square root of log n, and we discussed that both of these bounds are sharp. You can, of course, define discrepancy with respect to other families of sets. You can, for example, if you don't restrict yourself to axis parallel rectangles, you can consider rectangles rotated to in all directions. So, for example, instead of taking rectangles just like this, you also consider rectangles of this type. So in any possible direction. Okay, and then in this case, it turns out that the discrepancy satisfies these lower and upper bounds. And I remind you that the lower bound is a uniform lower bound, which means the discrepancy can never get smaller than this order of magnitude. And an upper bound means that there exist examples which actually achieve this order of magnitude. Okay, and you can see that, for example, in the case of rotated rectangles and circles, it's n to the 1/4 up to these additional logs. Okay, and you already see that the behavior is quite different. And when the family of test sets becomes even larger, when it's all convex sets, then the discrepancy becomes even larger, which is sort of natural. The larger the family of the sets is, the harder it is to be uniform with respect to every set. But you see two very different types of behavior. So for axis parallel rectangles, you have this logarithmic behavior. Here you have power behavior in the case of rotated rectangles or circles. Basically, in the second case, you have some sort of rotational invariance or curvature involved. And this is a general trend. Actually, I will not talk about the results. But if there are no rotations or directions are somehow fixed, usually the discrepancy is logarithmic. And if you have all rotations, or if you have some sort of either rotational invariance or a curvature involved in the sets in your test sets, then the discrepancy of the order n to the power 1/4. So there were several results of this type. There's still some work going on of this type, and these results also propagate to higher dimensions. So in higher dimensions, still for axis parallel boxes, you get logarithmic discrepancy. As we discussed last time, you don't always know what the exact power of logarithm is, but we know that it's logarithmic. Okay. And when you get to families with rotational invariance, you get some powers of n, and this power here is n to the 1/2 minus 1/2d. We briefly mentioned, and if you know some probability, it's quite natural to understand that for random sets, the discrepancy is roughly of the order square root of n. So here for rotated boxes and balls, it's going to be a little bit better than random. So the optimal discrepancy is a little better than random, and this improvement over random goes to zero as d goes to infinity. So for very large dimensions, the order of magnitude is almost the same as for random points. Okay, so actually we will, in these two lectures, talk a little bit more about this situation. So why does it happen that something is different when you have rotations involved or curvature involved. One of the reasons is that it's it's a known principle in harmonic analysis that if you have curvature, then you can say something about the Fourier transform. For example, if you take about the decay of the Fourier transform, and if you take, for example, the characteristic function of the ball, the Fourier transform of this characteristic function involves Bessel functions, and we know a lot about the decay. And this could be used in discrepancy estimates. This is something we'll do next time. So today I will not talk about one of specifically these two situations, but I'll talk about a very, very similar situation. I'll talk about points on the sphere and discrepancy with respect to spherical caps. And spherical caps are essentially balls, but on the sphere. Okay. So here I go immediately to the definitions. So assume we have a set of points, and my apologies, this is supposed to be FE, probably my picture, actually. Yes. Okay. Yeah, so in what follows, D will be the dimension of the sphere. So we live in RD plus 1. D is the dimension of the sphere. If you want to visualize what I'm talking about, just think about S2. Okay. So so we're considering endpoints on the sphere, so it's pretty much same setup as we had before. And the test sets that we will look at will be the so-called spherical caps. So the spherical caps are defined as follows. You fix one point x on the sphere. You fix a number t between -1 and 1. We'll call it the height. Okay, and then you consider all points on the sphere so that the inner product, dot product, is greater than or equal to t. So basically, that means you're cutting the hemisphere by hyperplane, which has direction x and height t. It's cut at level t. Okay, you get a spherical cap, so you get a ball on the surface of the sphere. Okay, and in this lecture, we will just deal with the L2 discrepancy. Of course, it's natural to define the extremal discrepancy and look at the supremum with respect to all caps, but we'll just look at the average with respect to all caps. Of course, it gives a lower bound for this supremum. Okay, so we'll look at this very specific L2 average, and we're doing the following. We're taking, for each fixed cap, we're taking the discrepancy of that with respect to that cap. Okay, and notice that the difference here is that compared to the last lecture here, I normalize the discrepancy. So I take the proportion of points from my collection that fall into the cap minus the area of this cap. And the area is normalized, so that's the total area of the sphere is 1. So we just divide by the area of the d-dimensional sphere. Okay. So basically, we're comparing two measures of the cap. Just the regular Lebesgue measure, normalized Lebesgue measure, normalized surface measure, and the counting measure, or the empirical measure, if you want. Okay. So this is the proportion of points. You count the number of points that fall into the cap. You count all of these points, divide by n. Okay. So both are probability measures. This is a probability measure in the sense that it's positive and the total measure is 1. And this gives you a probability measure, a discrete probability measure. So we're comparing this discrete probability measure with this uniform probability measure. Okay, and then we're just averaging over all of the caps. Okay, we're squaring this. This is an L2 discrepancy with respect to caps. And we're averaging over all possible caps in the following way. We're just averaging over all centers of the caps and overall heights of the caps. Okay. Okay, so I hope everything's clear what the cap is, what the setup is. Okay, one difference with the previous lecture that here we divide by n. So all the estimates will be divided by n. Okay. So if you want to understand what the cap says, if t is very close to 1, the cap becomes very small. If t is 0, the cap is actually a hemisphere. Okay, if t is equal to -1, the cap is the whole sphere. So I hope that's clear. Okay, and then I will go directly to the result that we will prove today. And this is a classical theorem by Joseph Beck, who's one of very big names in discrepancy theory, but generally not just in discrepancy theory. He's a big name in combinatorics. Okay, so and he proved that there is a lower bound for the discrepancy with respect to spherical caps, and this lower bound is of this order, n to the negative 1/2 minus 1 over 2d. Once again, I want to remind you that now we're normalizing compared to the previous lecture. So if you look at this here, this is the exact same bound that we've just seen for the rotated boxes and for balls. Because if you divide by m, you'll get negative 1/2 here, negative 1/2 here. So that's the exact same bound. It's actually quite interesting that all these bounds are the same. Unfortunately, we don't have any meta theorem which would say that all of these bounds have to be the same. Again, the methods of proof are somehow similar. For balls, you use Fourier transform. For actually, you can see that this situation is very similar. We consider balls in RD or spherical caps on SD. This is pretty much the same situation. However, as I said, we don't have a nice theorem that covers all the cases simultaneously and gives this bound in all of these cases. Yeah, although clearly that these things are somehow related. So Beck proved it in 1984 using Fourier transform methods. Using Fourier transform methods. There was together with Feng Dai, we have proved that, given another proof of this theorem about 10 years ago or so, using also Fourier methods. We used spherical harmonics and Gegenbauer polynomials. And then just about a year ago, together with Johann Brauchert from Graz, we have given a third proof of this theorem. And this proof avoids all harmonic analysis. So it's in a sense can be done by using just completely elementary methods, and I don't know if it's good or bad for an analyst to completely remove analysis from the proof, but or at least harmonic analysis. We'll still using some analysis, but this is the proof that I'm going to present for you guys today, and it's completely elementary. So I will present most of it. All right. So before I go to the proof, I need the first component. And this is a beautiful identity that the first time I saw it, I didn't quite believe it. And actually, one of the first times I presented it in a lecture, it was at a conference, and Andriy Bondarenko actually did not believe it either. He said, no, it can't be an identity. So I actually had to give him a proof and show that it is an identity. So this identity relates two different objects, the L2 spherical cap discrepancy that we just discussed, and the sum of distances between points. Okay. So let's look at this identity. Let's discuss what it means, and then we'll talk about its history and some implications. So this identity says that up to this constant, there's some dimensional constant, which is completely explicit, by the way, the L2 spherical cap discrepancy can be represented as a difference of the integral of the distance between 2 points. So the double integral, you can consider it to be an energy. Okay, so you have points. If I put -1 here, that would really be an energy. That would be the Coulomb energy, more or less. But here I have positive power, so it's just the distance integral. Okay, and here I have the same thing, but it is discrete sum instead of the integral. This discrete sum given specifically by these points. Okay. So you can interpret it in at least two different ways. First of all, well, discrepancy can be represented as the error of integration. So here you have an actual integral, and here you have a discrete sum, an approximation to the integral. You can view it as the Riemann sum given by these points. Okay. So this is one possible interpretation, but also you can say that this identity says that minimizing the discrepancy, which is what we want to do, is absolutely equivalent to maximizing the pairwise sum of distances between the points. Okay. If you think for it, if you think about it for a second, you can realize that this is actually not completely unexpected, because if you're trying to maximize the sum of distances, if you try to visualize it, you're probably going to get something uniform, although you have to be careful with such intuition. Okay, but this identity said that it's exactly the same problem. It's not just related problems, this is the same problem. Okay. Also, very often you can rewrite it, you can just add this to both sides, and then that would say that a constant times the discrepancy plus the sum of distances is a constant. So that quantity is invariant. No matter how you change the points, that's invariant. So that's why it's often called the Stolarsky invariance principle. There are at least several known proofs of this identity. It goes back to Kenneth Stolarsky, whom I mentioned in the previous lecture. It's in the 70s. Okay. Then there was a paper by Johann Brauchert and Joseph Dick in 2012, which was called the simple proof of the Stolarsky principle. And a little bit later, we simplified that even further. Actually, I wanted to call the paper an even simpler proof, but we added some other stuff. So paper is called differently. So this was together with Feng Dai and Ryan Matzke, and there was yet another proof roughly at the same time. So there was a lot of interest in this identity. The proof that we gave with Feng and Ryan is completely elementary, and actually that proof is problem number 1 in your homework that will be posted soon after the lecture, and it's broken down into pieces, but it's completely elementary. It's at the level of undergraduate calculus. Okay, you just need to do all the right steps, and you can prove this. You can prove this identity quite easily. So I'm not lying when I think that when I say that things are elementary. It's not like I'm using something as a black box. The black boxes I will use are also elementary. So this is elementary. You'll prove this in your homework, and you will discuss this in the discussion session tomorrow. Okay. There has been quite a lot of interest in the Stolarsky identity lately. It's been extended to various situations. A lot of situations mentioned here. This one is particularly interesting. So if remember, in the definition of the L2 discrepancy, we averaged over the heights of the spheres. So we took the mean over the heights. Well, if we take the median instead, if we take just height t equal to 0, remember height t equal to 0 corresponded to hemispheres. Right? So if you take just the hemispheres, then you get the exact same identity, but with the geodesic distance. So if you take the hemisphere discrepancy here, you would replace the Euclidean distance with the geodesic distance. It's interesting. This actually turns out to be a very simple observation, but somehow was overlooked. And then independently in the exact same year, myself, Feng, and Ryan observed it, and also Maxim Skriganov. Okay, so there has been quite a lot of work done on this identity. There are some very simple corollaries that you can deduce from this identity. So the first 2 are actually also your homework problems. These are problems. This is problem 2 in your homework. Easy applications of the Stolarsky principle. In particular, if you take your sphere and you take IID random points on the sphere, so uniform random points, then the discrepancy, the expectation of the discrepancy squared is bounded by n to the negative 1. Okay, in particular, if you take the square root, this will be n to the negative 1/2. Right, so that's exactly what we discussed, what you get for the random points. Okay, if you take jittered sampling, and you will discuss this in detail tomorrow, and also it's described in the homework, but roughly speaking, jittered sampling works in the following way. It's also a random point collection, but you first precondition the sphere, you divide it into pieces which are somehow almost equal. If it were in the cube, you could divide it into equal cubes. In the sphere, it's not quite possible, but you can construct things that are almost equal. And then you put one random point in each piece. Okay. So the points are independent and random, but each one lives in its own piece. In this way, you avoid clustering or big gaps. And turns out that in this case, the expectation of the this discrepancy squared is of this order. Okay, and if you take square roots, you get -1/2 or -1 over 2d. Okay, and that's exactly the bound. That's exactly the exponent from Beck's bound. So this shows that Beck's bound is sharp, because if the expectation is bounded by this quantity, then there exists a realization that has discrepancy of this order. Okay. So these are two very simple corollaries. There is an even simpler corollary from the Stolarsky principle. Okay, so this you will prove in homework. This just requires several lines of proof. It's very easy. But this doesn't require any lines of proof. This is obvious. Well, discrepancy is a non-negative quantity. So you have this difference. This tells you that this difference is non-negative, which tells you that the sum of distances is always smaller than the integral, no matter how many points you take. You expect that if the number of points is very, very large, this could approximate the integral very, very well, but it always approximates the integral from below. It's a fact that's not obvious at all. If I ask you to prove it directly, well, there are methods, but you need to go into some deeper theory, into positive definite functions, for example, which I'll explain a little bit at the end of the lecture. But there isn't a very easy way to prove it. And I think probably the Stolarsky identity might be the simplest way to prove it, to prove this relation, this inequality, this energy minimization, energy optimization, if you want, for this particular case. Okay, because the proof of this identity is simple, and then this follows immediately. Now, you can also go in one step further. You can replace this finite sum by any measure on the sphere. So if you take any probability measure mu, here I didn't write it, but if you take any probability measure mu, then you have this inequality. Among all the probability measures, the uniform measure is the best. It gives you the largest distance integral. Okay. It's very easy to see how this follows from the previous inequality, because, well, you can view this as the integral with respect to Dirac delta masses, okay, the average of Dirac delta masses, and then so for the integral with respect to a discrete measure, and then you can approximate an arbitrary measure with discrete measures in the weak star sense. That's very basic functional analysis. Okay, so weak star discrete measures are weak star dense in the space of all measures. Okay. All right. We will return to inequalities like that later, but now let's go back and try to prove Beck's theorem. We will actually not work with discrepancy from now on. We will just work with the energy. So we will use the Stolarsky principle, and instead I will try to prove the inequality, the lower bound for this difference of energies, the difference between the continuous and the discrete energy. Okay, so first I'll start working with this function, the Euclidean distance. Okay, so the Euclidean distance on 4 points on the sphere, you can obviously represent it this way. Okay, and then if I use x dot y as the variable, I have to deal with this function. Okay, and one very nice thing about this function is that if you write the Taylor expansion, the Taylor expansion has non-positive coefficients for all m starting starting from 1. Of course, the zero order coefficient is positive, but the zero order coefficient will not matter for us. Okay, but all of the coefficients in front of powers of t are going to be non-positive. It's very easy to check. I'm not going to do it. You can probably see it right away. Okay. If it were 1 plus t, they would be sign alternating. Okay. So these coefficients can be computed explicitly. Okay, and you can also compute their asymptotics. Yeah, I did not put this in the homework, but I would urge you to do it. It's a useful thing to do. Compute the asymptotics for the general binomial coefficient. Okay, and you can find out that they decay as m to the 1 over m to the 3 halves, which is nice because this means that this series converges absolutely up to the endpoints, which is good. It will be useful. So we can use this identity to express this function. Okay. As I promised, very simple calculus so far. Okay, so then we use the Stolarsky principle for the discrepancy. Okay, and so there is this constant floating around, but then we have the difference of the integral and the sum. Okay, and then we just plug in the Taylor expansion. And because the coefficients decay fast enough and the Taylor series converges absolutely, we can interchange integration and summation. So the constant term will go away because the constant term will be the same both here and here. Okay, and then we only have terms starting from m equal to 1. Okay, and then we will have, remember, I want now have positive coefficients. I put an extra minus here, so then that will flip these sums. So I have the sum of m's powers of the dot product. Okay, by the way, I sometimes will write dot product, sometimes I will use inner product notation. They're interchangeable, but they mean the same thing, I apologize. So, and then again, you have the difference of integrals. So you have the sum of powers of the inner products and the integral of the power of the inner product. Okay. All right, so now we want to understand something about these differences here. Okay, so we know that this term is positive, and let me go to the next slide. So just to summarize. So first of all, let's look at this integral because this is independent of anything. This is just a constant. What can you say about this integral? Well, if m is odd, it's quite easy to see that you'll get 0. Okay. Well, this is just an odd function, right? Over a symmetric domain, so that's 0. If m is even, well, you can compute it. It's a constant. You can compute it. Again, I would urge you to try. I think this particular one is not in the homework, but there are similar ones in the homework. Actually, no, I think it's in the extra problem in the homework. So you can compute it and you can find out the asymptotics. So if you have an even number, you get this is of the order that number to the power minus t over 2. Okay. So it's a direct computation. It would involve some gamma, beta functions, but it's not super hard. Okay. So again, everything so far is at the level of calculus, as I promised. Okay. So we have this representation where you have positive coefficients which decay of the order m to the negative 3 halves. Then you have this difference, and we know what happens to these quantities. Okay. Now, what we would really want to have is we would want to know that these differences are non-negative. Okay, why is that? Well, we want a lower bound, so if we want to estimate individual terms, we want to know that everything here is non-negative, and then we can work term by term. If signs change, then things might become really complicated. So this would be really an advantage, and it's actually true. Okay, so all of these terms are positive. And this actually brings us to another interesting topic, or even a couple topics. So I will talk about these terms now. So there is a very famous bound due to Welch, okay, which says that if you take unit vectors on on the complex sphere, so if you take complex unit vectors, okay, so it's vectors on the complex unit sphere, and you look at the powers of their inner products, okay, even powers of their inner products, and you take the average, you take a double sum and the average, so you take an average. This is essentially the same object as we have here. Okay, then you have this lower bound. Okay. In fact, let me jump to the end of the slide. If you take k equal to 1, so these are just squares, then this is also known as frame energy. So this arises a lot in finite dimensional harmonic analysis or applied harmonic analysis and information theory and signal processing. The minimizers of these sum, the cases when you get equality are exactly the so-called tight frames. I will not go into that topic, but that's also very interesting direction. It's a big theory, the so-called frame theory, which you might have heard about. Okay, and this inequality is actually pretty easy to prove. This is also in your homework. You basically need Cauchy-Schwarz inequality. That's all you need. Okay, and it can be proved in several lines using Cauchy-Schwarz inequality. Okay, and then to go from this inequality to this inequality, I mentioned this in the homework. I give you some hints and some references. You can use the so-called tensor power trick. If you don't know it, look it up. It's a very powerful tool that works in many different situations, which looks almost like pulling yourself out by the hair. You prove a simpler inequality, and then almost for free, you can have many other more complicated inequalities. It's really a powerful idea, which is very often used. Okay, so this inequality is actually sharp in the complex case, but it turns out that it's not sharp. You can improve it in the real case, and in the real case, you can have something that's very similar to what we just discussed about the integral and sums of distances. The discrete energy of this type is bounded below by the continuous energy. So this should be over SD. Okay. And this, again, can be explicitly computed, and you'll get this expression. And you can check that actually when k is equal to 1, both of these things give you the same bound, but when k is greater than 1, in the real case, this bound will be bigger. Okay. So there are lots of other inequalities of this type, but what I want to do now is I want to try to explain to you how you can prove these bounds of this type without going into too much theory. So I think it's possible to do it relying just on elementary methods. But we need a new notion. We will need a notion of positive definite functions. Hey, by the way, please feel free to stop me if there are any questions. Is everything clear so far? So going back here, this is a very rich and interesting areas. These inequalities are used quite a lot in approximation theory, and information theory, and samplings. So this is if you look at Welch bounds, so this is called Welch bounds. I think there is a Wikipedia page about them. This is a very well known inequality. Frames are also a very well known object. So my goal here is to give you some ideas about some of these topics and just to give you a very slight exposition of them. Okay, so now let's talk about positive definite functions. So for simplicity, our kernels will be continuous. So we have a function of two variables. Let us assume, I don't write it here, let's assume it's symmetrical and continuous. Okay, and we say that this function is positive definite if for any configuration of points in the domain of any cardinality, n is arbitrary, if you write down this matrix, this matrix is positive semi-definite. Or, in other words, so this is just the definition of what it means to be positive semi-definite. I'm talking about just the real case. Okay. All right, so it might be a little bit mysterious, this definition, for if you haven't seen it before, but there is at least one example that all of us know from linear algebra very well. So if our domain lives in Rn, and the kernel, this function, is given by the inner product between 2 points, okay, then this is a positive definite function. Because, well, the matrix that you will obtain here will simply be the Gram matrix, and Gram matrix is always positive semi-definite. This is what you know very well from linear algebra. Okay, well, but then you can use linear algebra to take this further. If I take any positive power of the inner product, integer positive power, okay, that will still be a positive definite. Why is that? Well, there is Schur's product theorem from linear algebra, which says the following. If you take two positive definite matrices of the same size, and you multiply them element-wise, this is called the Adamar product. So you don't multiply them as matrices, you just multiply each corresponding element. Okay. Then the new matrix, the Adamar product, is also positive definite. Well, which tells you if the Gram matrix was positive definite, now we have multiplied the Gram matrix with the same Gram matrix, you get the entries are inner products squared. That's still positive definite. So that's also positive definite function. Okay, and you can do it for iterated to any power. In particular, if you take any finite or infinite, whenever you have convergence, combination of these powers with positive coefficients, it's easy to see that it's still positive semi-definite, positive definite. It's a positive definite function, right? Just because it's obvious they form a positive cone. All right. It's actually, if you want functions that are positive definite on spheres in any dimensions, then they're actually exhausted by this construction. This is a classical theorem of Schoenberg. If you want positive definite functions on spheres in fixed dimension, you have more, but then we have to go into Gegenbauer polynomials, and I don't want to do it for this lecture. Well, we will only need this fact. We'll need this fact, which is pretty obvious and only uses elementary things, that these functions are positive definite. Okay. All right. So now I will slightly change the definition of positive definite. I will write an equivalent definition. Okay. So you can view if I define this energy integral with respect to an arbitrary measure nu. So I take my kernel and then put an arbitrary measure here and integrate with respect to x and y in that measure. I can call this the energy. So you can think about this as nu gives you some distribution of charged particles, and k gives you the interaction of those particles. And then here you're computing the total interaction. So this is the total potential energy of the interaction. So our definition is equivalent to saying that such energy integrals are always non-negative for any signed measure. Okay, basically the idea is the same as what I described before. If you write this discrete sum, you can write it as this energy integral for this discrete measure. Super easy to check. If you stare at this for 5 seconds, you will see it, right? So you get all possible pairs from the double integral. Okay, but then you can take an arbitrary measure and approximate it weak star by discrete measures. So if something holds for all discrete measures, it's also going to hold for all measures. Okay. So okay, and then with this definition, we can actually very easily switch to prove the following fact. It's actually almost an if and only if statement, but we only need one direction. I promise to keep everything elementary and almost self-contained. So assume you have a positive definite function, so continuous symmetric, rotationally invariant, very important. So rotationally invariant and positive definite function on the sphere. Okay. Then the normalized uniform surface measure, normalized Lebesgue measure, minimizes this energy integral among all probability measures. Okay, so in other words, no matter which probability measure you stick in here, the energy of the uniform measure will be less than or equal to that. Okay, so first of all, this is a very natural statement because it tells you, well, okay, it tells you that, well, if you put, for these kernels, if particles interact according to the law given by that kernel, if you put those particles on the sphere, then they will distribute themselves uniformly. Okay, the equilibrium position, the minimal energy distribution will be uniform. Okay, and it's natural to expect that in the electrostatic case, but here this theorem essentially gives you a very large class of functions for which it happens. Actually, the if and only if condition is conditionally positive definite. So basically you can change the constant. Obviously, the constant doesn't matter. Constant term doesn't matter for this theorem. Okay. In particular, this tells you that whenever you take discrete sums, okay, well, discrete sums, as we just said, are just energy integrals for a discrete measure, and sorry, this should have been just n to the first power. Okay. Okay, so that's bounded below by the integral of the uniform measure. Okay, so this looks very similar to what I said after we discussed the Slarsky principle. Okay, and here the inequality is reversed. So basically, another way to prove that property for the Euclidean distance was to show that the Euclidean distance is up to constant negative definite, because there the inequality was reversed. Okay, and well, we already know this because let's go back. We figured out that all the coefficients here are negative. Okay, well, again, except for the constant one, but we don't care. All the coefficients are negative, which in this expansion here, all the coefficients are negative, which means that if you flip it, this becomes a positive definite function up to constant. Okay, and because we know that all of these guys are positive definite. Okay, so yeah, so this gives you another way to prove. This also gives you a way to prove these inequalities. For example, now Venkap's inequality here follows, this follows immediately, because we know that this function is a positive definite function, as we just described, so the energy is minimized by the uniform measure. You get it almost for free from this statement. Okay, you just need to compute what the energy of the uniform measure is. Okay, all right, so this is the theorem. So any questions about the theorem? And actually, normally, when you look at this theorem, normally the standard proof of this goes into spherical harmonics and Gegenbauer polynomials. The addition formula for spherical harmonics, it's not super hard, but it requires some work. I want to give you a proof of this fact, which doesn't require almost anything. Okay, so I will. It will be just 2 lines or 3 lines, as you will see. We came up with this approach in the paper with Ryan Matsky and Alexander Vlasuk. I haven't seen this done before directly, but I think it probably exists in other papers. Okay, so here's the proof. This is the whole proof. Okay, so let me start with this quantity. So I'll take the energy of, so mu is an arbitrary measure, and I take the energy of mu minus sigma, of the energy of the difference. Okay, and because, let me go back, because of this definition, that for if the kernel is positive definite, this energy is going to be non-negative. Okay, because mu minus sigma is some measure. Okay, and this is non-negative. Okay, well, I write out what it is. This is just the definition. And then, well, it's a quadratic form, okay, with respect to the measure. So I expand it. So basically, more or less, I use the identity a minus b squared is a squared plus b squared minus 2ab, right? So this is what I use. Okay, so I'll get the energy of mu when mu hits mu. I'll get energy of sigma when sigma hits sigma. And then I get twice the mixed energy, okay? And everything's continuous, everything's finite. I can interchange summation and integration. So I will just start with sigma inside. And then I look at this. So now I recall that my kernel is rotationally invariant. So since it is rotationally invariant, it doesn't, and this is the uniform measure, it doesn't matter which point y I put in here. Okay, no matter how I choose y, because the kernel stays invariant under rotations, I'll get the same value. Okay, so this is a constant, but if it's a constant, okay, well, if I integrate the second time with respect to sigma, I should get ik of sigma. Well, so this constant has to be ik of sigma, okay, because this is a probability normalized measure. So this has to be this constant. And then afterwards, since it's a constant, the integral in mu doesn't really matter. So I can just erase it because mu is a probability measure. It just gives me that constant times 1. Okay, so I get this relation, and finally I get this. So this is a very interesting relation. So I started with this energy, and I got that it's equal to this difference of energies. Basically, it tells that even though this energy is a quadratic functional with respect to the measure, around sigma, it behaves like a linear functional. So this is what it says. Okay, but also I know that this is not negative. So that tells me immediately that the energy of mu is bounded below by the energy of sigma. Okay, so that's it. So I call this identity, usually I call this identity the magic identity, because this is just one of the implications. There are lots of implications that you can deduce simply from this very easy identity. Okay. And also it is related, you can take it further, it's related to the Stolarsky principle. And I think this is a very nice proof, very abstract and general, but at the same time avoids all complications that you might have had to deal with if you use spherical harmonics. Any questions here? Okay. Okay, so let me circle back a little bit. So we've proved this theorem, okay? And this theorem in particular, using what we know about using the examples of positive definite functions we have, this proves, actually it proves both the frame energy and Sidelnikov's bound right away. Okay, so we've proved these inequalities here. Okay, it's very easy to compute that the integral is 1 over d in the case of the squares. It's a very good elementary high school problem. Okay. By the way, just a little warning. In this case here on this slide, d stands not for the dimension of the sphere, but for the ambient dimension. Just because in this theorem I did it, these are pretty classical results, and I didn't want to rewrite them, replacing d by d plus 1. I wanted to write them in the classical form. Okay, everywhere else, since we're working on the sphere, for simplicity, d is the dimension of the sphere. Okay, so remember why we did this, because we had this relation and we wanted these terms to be positive. And now we know the answer is yes. Okay. Now we know that the Sidelnikov-Benkov bound actually tells us that these quantities are greater than these quantities. And in the case of odd powers, well, because this is a positive definite function, this is just greater than or equal to 0. Okay. And 0 is the value of this integral. So all of these terms are positive, which is super nice. I have only about 10 minutes left until the end of the lecture, but in these 10 minutes, I will finish the proof. I will actually finish the proof on one slide. So now we know that all the terms here are positive. Okay, so if I want a lower bound, I'm allowed to throw away as many terms as I want and just estimate the terms that I'm left with. This is exactly what I'm going to do. So let me jump forward. Okay, so this is the end of the proof of Beck's bound. Okay, and it's all the steps are described in this slide, and it will only take me just a few minutes to go over them. So please bear with me. This is it might seem a little bit technical, but it's actually quite easy. Okay, so here's what I'm going to do. I'm going to work in I'm going to start throwing away things. Okay, so first of all, I'm gonna throw away all the odd terms. Okay, so that is reflected here. So I'm keeping only the even powers. Okay, for the odd terms, I just know that this quantity is bounded below by 0, so I throw it away. Okay, now what else do? I will throw away all the even terms, okay, starting from, well, below some threshold capital M. Okay, we'll figure out what the threshold will be. So we'll just start our summation here with capital M. Okay. And then I look at these sums. Okay, so now I want to estimate. I cannot just estimate everything by zero. Then my lower bound will be zero. I need some non-trivial lower bound. Well, this non-trivial lower bound will actually be quite trivial. What I'll do is I'm going to throw away all the off-diagonal terms in this sum. So I'll only keep the diagonal terms. So that is I is equal to j. If I keep I equal to j, the dot product will be 1. So I'll just get ones. And I can, so here's the thing, I can throw away off-diagonal terms because I'm dealing with even powers. And so all the terms here are positive or non-negative. Okay. I couldn't do this with odd powers because some of the inner products could be negative and their powers would be negative. But this is even power, so everything's positive. I can throw things away. Okay, so I will be left just with the diagonal terms, and the diagonal terms give me there are n of them. So it's I equal to k, or sorry, j equal to k, and there are n of them. So each one gives me 1. I have n, 1 over n squared times n times 1. So 1 over n. This is what I get. Okay. Okay. And now I have the value of this integral, which we discussed, and I can, since all the terms are bounded, I only take terms with small r, I can bound this from below by some constants over m to the d over 2. Okay, so now I want to take m large enough so that this is, say, smaller than 1 over 2n. Okay, so which would mean that I need to take m of this order. So if I take m of the order n to the 2 over d with appropriate constants, this would be of the order 1 over n. So if I play around with constant, this will be less than 1 over 2n. Okay, so make constant large enough. Okay, it will be less than 1 over 2n. And so this term will be bounded by 1/2 1 over n. Okay. So this will be independent of r. So I just need to compute this sum. Well, you just use the integral test, right? So this is of the order, you start from m. This is of the order m to the negative 1/2. Let me also color code this. Okay. But now we recall that we've taken m of this order, okay, and we plug it in, and we get exactly what we wanted to get. So that's it. That's the whole proof. Okay, so this is the proof that we found together with Johann Brauchert. This proof can, at this level, if you just want to get at the bound, it's absolutely elementary. And as you see, modularly, some of the components that we use, the proof fits on one slide. And essentially, this is just calculus. You just use Taylor series. That's it. So we're not using any non-trivial facts about the Fourier transform. We're not using Bessel functions, not using spherical harmonics and behavior of Gegenbauer polynomials. So it's a very, very nice elementary proof. You can push this proof even further. You can get constants very close to optimal conjecture constants of some dimension. You can get very exact values of constants here. Right now, I was very sloppy with the constants. I always used this symbol. I didn't care about them much, but you can be careful and run the proof a little bit more carefully and get very good constants. Another thing about this proof is that when you look at it, when you look at things that I was throwing away, you would probably say, well, this proof is super lossy. This cannot possibly give a sharp bound. And yet we know that this is actually the sharp bound. Well, jittered sampling, which you'll do in homework and in the problem session will tell you that. So this is a sharp bound. So how could that be? Let me try to just talk, give some heuristics. Well, so the first step was threw away all the odd terms. Well, that might be lossy, but it's really not, because if your set of points is symmetric, so if it has an even number of points which are symmetric, then this sum this sum here will actually be 0 because this is an odd function, so the sum will be 0. So that might not be so lossy because for symmetric sets this is 0 anyway. Okay, now you've thrown even terms up to some number m, where m is of the order n to the 2 over d. Okay, that's a little bit more interesting. So first of all, this is interesting in the following way. Notice that usually when you try to estimate something using Taylor series, you usually keep the first few terms of the Taylor series and throw away the remainder. What we do here is the opposite. You throw away the first few terms and you keep the remainder. But it's not surprising that you should throw away the first few terms, because initial terms can also be 0. Because look at, okay, this is a polynomial function. Okay, so you have the difference between the sums of points, and you have a polynomial function, and the integral with a polynomial function on the sphere. Well, objects like this are actually very well known. So these are called spherical designs. So this can be 0. So a spherical design is a set of points on the sphere such that for all polynomials up to a given degree, the average over the sphere is equal to the discrete average. Okay. It was known for a long time that a general they exist, but the optimal bound was not known for a long time. So this was actually, I think this is very appropriate to mention this paper here. This is the paper by 3 Ukrainian authors, Bondarenko, Danila Bondarenko, Andriy Bondarenko, Danila Radchenko, and Marina Vyazovska. So actually, this is the first annals paper of Marina Vyazovska in 2013. They solved the conjecture of Krivar and Meyer, which said that there exist spherical designs of this order. So the smallest spherical designs that exist are of this order. Okay, and it was conjectured for a long time, and this conjecture is actually very logical because, well, if you want to find a spherical design, you need to solve such equations, right, for all polynomials of degree up to m. Now, if you look at the dimension of the polynomials on the sphere of degree up to m, it's exactly of this order. It's easy to check if you know something about spherical harmonics, or even if you don't. You can see it. Okay, so then the conjecture was, okay, that this essentially is solvable. That is enough. So having that many points would be enough. And they solved it very elegantly. It's a very nice paper. Also, I think it's maybe 12 pages long, and modular some preliminary facts can be presented in one lecture. Also, it uses fixed point theory in a very interesting way. So I really recommend that paper. Okay, so this says that if this is the optimal order, so we can take m of the order n to the power 1 over d. So up to that order, these things can be equal. So back in our proof, up to that order, these things can simply be 0. So these things here, they can simply be 0 if you take a spherical design. Well, okay, we're not going up to 1 over d, we're going up to 2 over d. So I don't have a good theorem about this yet, but this doesn't change things too much, but apparently the difference is not too big. So, but if we went up to 1 over d, this could simply be 0. Apparently, if you go up to 2 over d, these differences can still be small. Okay, so this is basically the end of this proof. I just want to, well, as I mentioned, I will not go into details, but there are some conjectures about the constant, and this method gets you very close to those optimal constants in the conjectures. And in the last minute, I'll just mention some geometric corollaries from these inequalities from this proof. Okay, so remember the proof was that we know that all of these coefficients are positive. Okay, so basically, all of these are positive. So what I can do is just throw away all the terms except for one. And what I can do is take the discrepancy and estimate it by any one of these terms. Okay, so the very simple adaptation of the proof. So just estimate it by one of the terms. They're all positive. Okay, well, let's see what we get. So there are, for low values of m, you can find nice geometric interpretations. Okay, let's take m equal to 1. Okay, if you take m equal to 1, well, this is 0, as we know, it's an odd number. But then this sum here, it's very easy to see that it's the inner product of these two sums. In other words, it's the norm squared of this sum. So it's the norm squared of the mean of the n points, or in other words, the center of mass of the n particles or n points. Okay, so this tells you that discrepancy is bounded below, so now we take square roots, by some constant times the norm of the center of mass. Okay, yeah, so very easy. And a statement of this type is actually very, very reasonable, because this says, okay, if our points are very unbalanced, if the center of mass is somehow far away from the origin, then the discrepancy should be large. Okay, makes perfect sense. If this center of mass is big, then points cannot be very uniform on the sphere. However, I searched the literature and I never found any inequalities of this type anywhere. This proof gives you this inequality almost for free. Okay. And there is a further adaptation, the frame energy that I mentioned. Notice now our ambient dimension is d+1. Okay, if you take the term with m equal to 2, okay, this integral will be equal to d+1 over d+1. It's easy to check. And then the energy is bounded by some constant times the difference between this discrete frame energy and this number. And we know that you get this is equal to 0 if and only if you get a tight frame. Okay, so in particular, it tells you that if your set is far from being a tight frame, then discrepancy is large. Again, so if it's the uniformly distributed sets have to be somehow close to tight frames. Okay, so I will stop here. This is the end of my lecture, so I went over time for by a couple minutes. My apologies. Thank you very much for listening. Yeah.